Welcome to Lecture 3.2. As you remember, we spent last week talking about this thing called a derivative. And before we go on to some tricks for finding them and when they're used, we need to talk about something called differentiability. So the next 3 lectures are going to be about the existence of the derivative and how can we be really precise about it. We'll also look at some technology skills starting tomorrow, something called the ender function on your calculator. Here's where we start. So this is a pretty simple question, right? Calculate the derivative of a function at -1. Only when we go back and look at the function, you'll realize immediately that in this class, we've never taken the derivative of a piecewise function yet. Well, you know the definition, so let's see what we can do. Here's how I would start. The derivative of f at the point -1, or the x value -1, should be just the solution to this limit, right? That's the definition of the derivative. It's the slope, and we approximate the slope by taking the limit of the difference quotient. The only thing is, when I go to solve this limit, I now run into a problem, because my next step would be to take x plus h and plug it into the function f. But with a piecewise function, I have to choose. Which function should I choose? Well, I took my function, and off to the side here, I've just kind of sketched what it would look like. Piecewise function, we've got 3 sections, and the dividing lines are at -1 and +1. So if I'm trying to find the limit of this, whatever it is, at -1, the truth is I can't just use one of the 2 function equations. This limit is going to have a different function coming from the left and a different function coming from the right. What that means is we actually need to expand our understanding of what the derivative is, and this is where the definition of derivative is going to rely on what you already know about limits. And it turns out we're going to have to talk about a right-hand and a left-hand derivative. And it's easy to see that the only way the derivative exists is if this limit exists. Well, the definition of a limit says that this limit only exists if the left-hand and the right-hand limit equal the same thing. So to calculate this derivative, I'm going to have to actually find both limits. Here's what the setup would look like. On the left-hand side, I'm going to use the function that's on the left, which is this top one. On the right-hand side, I'm going to use the function that's on the right. You can see what the limit's going to look like. You've done this process a million times. Go ahead and work it out, and I'll do the same. And so when we work these limits out, just using our normal limit properties, it actually turns out that we end up with 2 different numbers. That means the limit doesn't exist. But more importantly, this wasn't just any limit. This was a limit of difference quotient, and that means that it represents a derivative. If this limit doesn't exist, then actually that means the derivative doesn't exist either. To be specific, we would say the derivative at -1 doesn't exist. This function could have derivatives at other points. It just doesn't have one at -1. Let's talk about f prime of 0. You can imagine how it would be set up. Something like this. Now, at 0, and you'll notice that I put in the 0 right away here. That's okay. You could put x there if you wanted to. What's important is at 0, we don't have to make any kind of decision. 0 is right in the middle of x squared. There aren't 2 different functions. So in this case, I don't really need to think about the limit on one side and the other side because I can just take the limit of the x squared function. It would look like this. And the answer to the limit is just 0, which means the derivative of f at 0 is 0. Let's try the last one. Right, so as you may have realized, this is going to be one of the ones where we have to consider the 2 sides separately, and that's because 1 is a boundary point. Right here at 1, we switch from the x squared function to the linear function. Now, I also want to clue you into a really important detail that I skimmed over before. Technically, f of 1 in either of these limits refers to the actual function. In the actual function, where do I plug in 1? Right, I plug it into the middle function. So the actual f of 1 is 1, because 1 squared is 1, and that's the output of the function. And that number 1 is what I should put on both sides. If you ever see that one of the two sides doesn't equal the same number, for example, right here, when we get really, really close to x equals 1, the x values here, 2 times 1 minus 1, also equal 1. If they didn't, we would have to say the actual number that they do equal. And technically speaking, we couldn't plug that number in, so we might even have to write a does not exist. In this case, however, we're lucky because both sides approach the same y value, and so that's the y value that we put, and then we continue with the limit as we do normally. The work looks like this, and this time we're in luck. We do get the two-sided limits equaling the same value. Because the right hand and the left hand limit equal the same, this limit exists, and this limit equals 2, which means that the derivative of this function at 1 equals 2. Sound good? All right, try one for yourself. Right, so as you saw in Edpuzzle, it turns out both of these derivatives don't exist, although for different reasons. The first one doesn't exist because the right hand and left hand limits don't equal each other. One of them equals -1, and the other one equals -infinity. The second limit, I mean, obviously if the two sides don't equal each other, then the limit doesn't exist, which means the derivative doesn't exist. The second one was the derivative at 0, and actually this one gets stuck even sooner in the process because at 0 the whole function doesn't exist, which means that it doesn't really matter what limits I set up. There's nothing I can put in right there, and so I can never solve this limit no matter how I rearrange it using different equations. There's no y value at 0. So this kind of makes you want to wonder, what does it really mean for a derivative to not exist? Well, I'm so glad you asked. It turns out there's 4 different situations in which a limit might not exist. We'll start thinking about it graphically, and then we'll talk about the algebra. So the 4 different things that could happen that would cause a derivative to not exist are a corner, a cusp, a vertical tangent, or a discontinuity. You have seen all of these things except for a cusp before, so that's the only one I'm going to explain. I expect you to read the definitions and be able to apply them coming into class tomorrow. Let's talk about the cusp. There's a lot of ways to see what's going on here. It's kind of a special case of a corner where the slope is just different on either side of the value. But a cusp doesn't just have a different slope on this side and on this side. In particular, one side is approaching a slope of -infinity, and the other side is approaching a slope of +infinity. So make sure that you can see that happening. Pause the video here to write these definitions down and add them to Cram. When you press play, we'll talk about a quick check for understanding. Great, so take a look at this funky graph. It's a very strange function. Who knows what the equation's going to be, but you've got a graph. And in particular, your graph has 4 weird points. We're calling them point A, point B, point C is right here in the middle, and point D is right there. Tell me, at which of these points does the derivative not exist? And classify why. You should be looking at your notes and the 4 different types that we just talked about. Great, so hopefully you saw in Edpuzzle that A is a cusp, and I see that because coming from the left-hand side, the slope is approaching +infinity. It's getting positive and positive and positive, and the slope's getting higher and higher and higher. On the right-hand side, the slope is approaching -infinity. The slopes here are all negative, and they're becoming higher and higher negative numbers. That means at A, the derivative doesn't exist. At B, this is a kind of tricky one. At B, this is a discontinuity. The limit does exist. The slope actually looks the same on both sides, but because that's an open hole, it's a discontinuity, which means the derivative does not exist. At C, the graph looks great. It's nice and smooth. The limit exists, the actual function exists, they all equal each other. At C, it does have a derivative, no problem. D is clearly another case of a discontinuity. This function does not have a derivative at point D. So let's be a little more precise. We need a real definition, and we use the word differentiable to convey this idea of the derivative existing or not existing. I'll give you the formal words and then I'll explain what it means. We say that a function f of x is differentiable at a point A, if and only if, this IFF means if and only if the derivative exists. Okay, duh, that seems simple. What does that really mean? Well, this derivative is the same thing as this limit. So when we say that f of x is differentiable, we're basically saying that this limit exists, or we do have the alternate definition if you prefer to think of that one. Algebraically, what are you going to see that tells you something's differentiable? Well, we just did a couple of these. Algebraically, you're going to see that the limit of the difference quotient exists. The right-hand side and the left-hand side limit, they both equal the same thing. Graphically, what you see if a function is differentiable at this point is that the tangent line exists. And usually that's because the graph is smooth. Think about that last example. The only place where this function was differentiable was C. How would you characterize C? How is it different than the other places? Well, the function's kind of smooth there. And another way of saying that is like saying that the slope is the same on both sides of the point and that the point is defined. Pause the video here to make sure that you have this definition written down. And not only should it be written down, but you should really understand both the algebraic idea and the graphic idea. You should be able to say them back to me when I cold call you at the beginning of class tomorrow. Okay, here's why these ideas are so important. We're getting to my favorite type of math. We have this humongous gray area. And I'm going to relate this gray area when it comes to differentiability to two gray areas that you already know about that you may or may not be thinking about. Remember way back when we first learned about the limit? There was a difference between saying that the limit doesn't exist and saying, well, we don't know what the limit is. There were all those strategies that we had up on the board during the Socratic. Those strategies, hopefully, were going to help us figure out that the limit existed. But sometimes when we didn't know what strategy to use, we had to make a decision, and we had to decide either that the limit doesn't exist or that we just don't know. That decision, that judgment call, that's the gray area here. And when you get really good at this topic, when you have mastered it and are ready for the AP exam, you should know the exact contours of just how much you know and just how much you don't know. Similarly, with continuity, there was one thing which was to be continuous at a point, or not continuous, and then there were a lot of functions for which we just didn't know. Think about the definition of differentiable that we just talked about. Can you tell me exactly what it would mean to know for sure that the function is not differentiable? How is that different than just not having enough information? Here's how I would characterize it. The definitions that we learn about the right-hand and left-hand limit are the foundation for all of these. If the right hand equals the left hand, the limit exists. If it doesn't, the limit doesn't exist. If we don't know, that's when you're in the gray area. Similarly for continuity, the right hand limit has to equal the left hand limit and the actual function. If you know it does, or if you know it doesn't, then you can feel really secure, but sometimes you won't know enough information to either confirm or deny, and that's when you're in the gray area. For differentiable, it's not just any limit that we're talking about, it's specifically the limit of the difference quotient. I'm going to end this video with a really fun trick, and I'll actually leave it as a challenge for you. There's something called local linearity, which is when a function looks like a straight line when you zoom way in. And it's kind of a quick way to tell if a function's differentiable. We'll talk about why in the next video. But before you close this out, take a moment, grab your graphing calculator, and graph both of these functions in the same viewing window. And then zoom in. And zoom in really, really, really close. Use the trace button to jump back and forth. You should notice a difference. Can you tell which one of these is differentiable? Let's talk in class.